They're all working? All right. Thanks for coming to September's meeting. Just real quick before we get started, one quick announcement. It's tomorrow and Thursday, but there is still time to get tickets for progressive FSharp tutorials, so I thought I'd put that one out there. It's 2 days. It's a good time. Some of the people who are in the room tonight are actually going to be leading sessions there. Find me later to ask me more about it if you want. Jack's going to do a talk for us for a little while, and then we're going to have Rachel do a talk. So, all right, go ahead, Jack.
Okay, thanks, Paul. So this is a very condensed version of a talk I gave at Lambda Jam a couple months ago, and it's about functional linear data structures in FSharp. I'll tell you a little bit about how I came to this talk, actually. Some years ago, I pulled off the shelf one of my hobby projects and started going through the code refactor loop. And what I found was what I was getting as the code that I was reusing was all these functions that I was passing around in C#, which is kind of a pain. And it was starting to hurt my brain because delegates just didn't seem natural. And I'd heard about FSharp, and it was a functional language, whatever that is. It must mean that my functions will work, and this problem I'm trying to solve will be better in FSharp for some reason. So I went about learning FSharp, and at some point I stumbled across Chris Okasaki's thesis on functional data structures, and found it really interesting. And that was kind of one of my paths into learning FSharp was through purely functional data structures. And in doing that, I then got involved with the FSharpx open source project, which is a foundational library for FSharp. If you're not aware, it's available in GitHub and also on NuGet. And I started noticing some things about the linear data structures that I thought were really interesting. So I put it here in kind of a data science-y format that functional linear data structures form a semantically coherent set. So I'm going to tell you what I mean by that in this talk. I think most people who code in a functional language, whether it be FSharp or something else, they rely heavily on the singly linked list, which is really the foundational data structure of all functional programming, I think. But there are actually other constructs that you can use. Sometimes they turn out to be better for a particular task, even though you can do virtually anything with a singly linked list. However, it may not be efficient, both in terms of computation and also in terms of the fluency of the code that you write. So I want to take a look at the characteristics of what a linear data structure is and what it does. Starting with order, the order of your linear structure is usually by construction. Okay, that's pretty much what we're all used to. But I want to open up your minds to, it could also be some other things. It could be, your order could be sorted, or it could be random. Haven't actually seen anything random, but I've imagined linear data structures that could implement randomness. So the construction is either how it was originally constructed or all the elements that get const to it as you grow the structure. Evaluation. In FSharp, everybody's probably aware that evaluation is eager by default, and you actually have to go out of your way to get lazy evaluation. And we'll take a look at how lazy evaluation is used and what it's actually good for, at least in terms of linear data structures. Peak is fundamental. I mean, you have to look at the data. And in the case of the singly linked list, you can see the first element, which is the element that you last added by not coincidence. But there are other structures that let you peek at something else. Maybe you can peek at the last element, or maybe you can peek at any element through an index. And you can actually combine these. Like maybe you can look at the first element and the last element, but not the ones in between. Then there's also construction. And so construction kind of theoretically is not a necessary characteristic, because maybe you end up with just a functional data structure that is static, that you can't append anything to it. That's what you got. And so I frequently see that with people that, for instance, it's kind of common to wrap an array in some more code to make it local and make it immutable. And at that point, you can't really add to it. You're stuck with the array that was originally loaded. Construction, once again, maybe you add at the beginning, maybe you add at the end, maybe you can actually insert into it. And of course, when I'm talking about adding to it and inserting things like that, we're really, since we're talking about purely functional, we're talking immutable, so you're actually getting a new object at the end of the whole thing, and not updating the existing one, of course. Removal or deconstruction, with the linear list, so you deconstruct by taking head, tail, throw away the head, you have just the tail, and you can deconstruct down to an empty list. And with the list, you just do it at the beginning once again. It doesn't have to be that way. So there's one characteristic that overrides everything else. It's really the unifying theme of linear data structures, and it's, in the case of FSharp, it's seek, which is really IEnumerable under the covers, and it's what allows us to compose one structure into another. So here's a whole bunch of different linear data structures. Array, of course, is actually not purely functional, but the way FSharp works, it is very composable, so we can compose it here with the other data structures. You wouldn't actually want to do anything like this, but it does show you that you can start with a sequence, start composing it through all the different linear data structures that you might have available, and at the end you have the same sequence, because that's how sequence works. The other advantage of sequence, the way it's implemented in FSharp, is that you also then have 68 seek module functions that are available to any one of your data structures. Your data structures all implement seek, so they have all these module functions available to them. Things like aggregate functions and folds, map, etc. The one thing you won't be able to do, however, is any kind of function that requires reversing the order of sequence, at least not conveniently. I've seen some kind of strange code before, usually in Haskell or something like that, where they actually do a fold back on a sequence, but it's makes my head hurt, so I don't want to think about how to do that. And here's another thing that sequence gives us: the ability to unfold sequences through means of some algorithm, and we can actually unfold sequences up to infinity. And because sequence isn't really a data structure, okay, it's just I'm not sure what word to use to describe it. It's a placeholder, okay. It sets up your computation for the linear structure that you have. It doesn't actually execute it. That doesn't get executed until you instantiate it into a real live data structure like list. So what are the kind of things we can do with this capability to create these infinite unfolds of an algorithm? We can do things like a Markov chain, for instance. And this is a real simple one. So we define a type of weather, and it's real simple. It's either sunny, cloudy, or rainy, and we have a function that implements a match that takes what the weather is today, takes a probability, runs it through this match, and it predicts the weather for the next day. And that just goes on to infinity. We can have this model that will model the weather based on these probabilities that we have essentially made up for the current weather. And here's how you actually do it. I've added some extra code in here for demonstration purposes because this is a demonstration when there's some things that I want to point out in it. So, for instance, this would not actually run to infinity if we just unleashed it, and that's because I put a counter in here. And it's a long integer, so it'll take a long time for it to blow up, but eventually it would blow up. The counter here is so that in the display we can see what element we've actually run through our computation. And so it's just taking today's weather, bringing in a random number generator, and then we put it through the function that we just defined on the previous slide, taking the next random number that it generates, and that's the next day's weather, and repeat and rinse. And in the middle here, we're going to print some information so that we can keep track of what's going on. And then finally, we have a print statement that instantiates this to list. So now we've actually performed the calculation. In this case, we're going to take the first 5 days of our forecast, and there you have it. So sunny, sunny, cloudy, rainy, cloudy. But there are no shortcuts down the infinite road. And this is why I put the print statements in there to demonstrate this. So even if we want really just to calculate, some sequence in the far future, we still have to calculate everything leading up to that far future. And so this is a demonstration of that. So even though we are skipping the first 5 days of the forecast, and then we take the next 5 days, computation actually has to work through all 10 instances. And so this brings up another point about this whole exercise of unfolding infinite sequences, which is there are some things that you cannot do with infinity, like take its length. Okay, so don't try to do that, and don't try to instantiate the entire unfolded sequence to an actual structure, because that also will not return ever. So let's take stock of what we've looked at so far. Talked about linear structures as an abstraction, okay? And the unifying theme of these structures is the sequence. That lets you orient yourself as to where you are, regardless of which structure you've actually implemented to. And the sequences are sequential. You can't skip ahead of them. You got to do the whole sequence. So we're going to look at some more possibilities that we can use in terms of linear structures and why we want to use them. And the first one is this this problem with using sequence for probabilistic calculations, and that is not idempotent. Okay, it's not guaranteed to give you the same results twice. So if you wanted to use the same sequence that you had set up more than once, it's going to return different results every time, because this was a probabilistic calculation. If it wasn't probabilistic, not a problem. So what can we do about that? This is where lazy list comes in. And some of you may be aware of lazy list. It's available in the Power Pack, along with it's in some other libraries too. An implementation of it is in FSharpx. There's one in the Xcore library as well. I think there's a few others floating around. They're all, I think, pretty much derived from the original Power Pack implementation. And what lazy list does, it acts sort of like a sequence, in that we'll also unfold these infinite sequences for you, and it also is a list. So it's actually list-like. It's structured exactly like a list. You can const onto it and take its head and tail, etc. But what it does is, first, once you actually go to one of its elements, that gets cached, essentially. So it's never going to change. So in the case here, we can take the first 3 items from our lazy list, generating it with a lazy weather list, and then later, we decided we really want the first 4 for whatever reason, and the first 3 are always the same as they were the first time. And the same rule applies to lazy list as applies to unfolding sequences. There's no shortcuts. It's always going to force you to evaluate everything up to the point where you're really interested in the data. Another good thing about lazy list, and actually many of the alternate linear structures, is it's got a constant time append, which you don't have with a list, as you might be aware. So in this case, we make a list of observed weather, and we want to combine it with a list of predicted weather. This might be something you're interested in doing in your own modeling, for instance, whether it's weather forecasting or modeling the stock market or any kind of sequential modeling, where you might actually want to append observed data and some sort of predicted data for whatever reason. This is an example of doing that. And so in this case, we're taking the observed weather list, and we're appending it with the lazy weather list down there, and then we're skipping 4 and taking the first 3, and you can see that as it should be, we get 1 element from the observed list, and the rest are from the predicted. So what lazy list is doing is it's implementing, as I said before, a list-like data structure. And this brings us to the second big thing that is common between all these linear data structures. So the first one is they all implement seek. Okay, so, and the second one is they implement this head and tail signature. Okay, so this is one the other unifying semantic element that I wanted to kind of hammer home to everybody about using alternate linear data structures. Is they work very much like lists in very many ways. They're sequences. They implement this head and tail signature, and we're going to see one that implements the dual, actually, of the head and tail signature, which is kind of interesting. List is list. It's how, like I said, it's the foundational data structure of functional programming, but it's not necessarily how people think. Okay, we don't think usually in terms of, I've got a list and I'm going to add an element to its beginning. I mean, humans usually think, I have a list and I'm going to add an element to its end. So we have a structure for that. And this was implemented by Stefan Forkman in the FSharpx library. It's actually from Clojure. I'm assured that it's actually the same, basically the same implementation, which is it's a hash map. It's a hash map or a hash array map. Try. It's very fast. Let's put it that way. And it not only inverts this head-tail signature, but it also lets you have lookup and update capability by index. So it's not just the case with all the list-like structures where you can only ever peek at the first element. This one, you can look at any of them. It acts really like a vector because it's anchored at its beginning and it grows and shrinks like this, okay, at the end, which is kind of how we think about lists growing and shrinking, not necessarily how the computer does. So one of the things you might want to do with vector or any other linear data structure is implement a composite data structure, like a multi-way forest. I've also seen this called, a rose tree forest, another name for it. But essentially, this is the kind of thing that you run into with XML, HTML, arguably JSON too, where you've got sequential structures that act like the top node, where each element is the top node of a tree of more sequential structures. So you could actually implement these segments of sequences in any linear data structure, whether it's a list, a lazy list, a vector, or any of the other ones that we might see. But in our case, we'll say that they're vectors. So it's, the definition of this type is actually a recursive type. So it's a node with an element at the top, and then children in a multi-way forest. And multi-way forest is defined as a multi-way tree of vector. And then we got to create, we can create a singleton. Now at this point, I wanted to introduce, we're going to put that aside for just a second and talk about a couple more data structures. And notice that these also implement the head-tail signature of list. I think it's not an accident that head-tail seems to be the most common of the signatures, whereas vector is about the only other structure that implements the dual of this signature. But Q, it's probably familiar to you. It's just like queues in imperative programming languages. It's first in, first out. DList is a little more complex and interesting. It shares some characteristics with Q. It can act as a first in, first out, because you can, you can construct at the end and pop it off the beginning, but you can also construct it at the beginning. And the other thing that distinguishes it from a queue is at the construction at the end there, you can do not just a single element, but you can do a whole nother DList. So it'll append a DList. And as I was saying, a lot of these alternate linear data structures implement constant time append, which is a real convenient thing to have sometimes. And so I'm going to show you something that we can do with these two structures. Taking our multi-way tree example, we can implement by transforming from one data structure. In this case, we're going to say it's a vector, which is the segments of our multi-way tree. We're going to transform it to another data structure and use the characteristics of that data structure to implement an algorithm that otherwise would be, at least a couple lines longer than this, I'm sure. And then the final structure that we output is actually the queue structure, the first in, first out structure that we talked about. So let's take a look at how this actually works. We want to initialize our recursive loop with an empty queue, so that's what we start out with. We, because everything adheres to the rules of seek, so we can just do a simple of seek load into a new DList from the top level segment of our forest, and we're off to the races, so to speak. So we've got a loop with a match of that DL structure in there. And so what we do is we decompose it into head and tail, which we talked about. The head then gets enqueued into our resulting queue, so we know that everything's going to be in the right order. And then for that head element as well, we take its children. We do another load of that vector into a D-list. We append it to the D-list that we're already working with. Okay, and we loop through again. Rinse and repeat. We keep taking the head and queuing it into our final data structure. Take its children, append it to this working data structure that we've got in the middle. And it's essentially, I mean, the whole guts of the thing is one line of code to do a breadth first traversal of the white tree. So that was kind of the big story that I wanted to tell you, which is, through composition and using alternate linear data structures, you can perform, some algorithms that might otherwise require writing code rather than just using the characteristics of these data structures to get through. And there's a few things we haven't talked about, so I'll get to those as well. There's another data structure. This is one that's actually described by Okazaki, both in his thesis and in his book. By the way, his book is, for those of you not aware of it, it's I think it's called Purely Functional Data Structures. That's what it's called. And it's a very popular functional programming book. You can find it on Amazon. It's a big seller, actually, for a technical book. But you can see this is actually the dual of a vector, which we talked about. And actually, I implemented this in FSharpx by tweaking some of the vector code that Stefan wrote, and it works. It's just a dual of vectors. So this will give you actual list-like features, as well as indexed update and lookup into any element of the structure. Then there's a double-ended queue. This one is kind of cute because it actually implements both the signatures. So we've got the list-like signature and the vector signature of last init. You can construct and deconstruct on both ends, so you can shrink and grow it like this, and it's really perfectly symmetrical. But there's actually a performance price. It's really hard to get double-ended queues right from an implementation standpoint. There's going to be some situations where it's not going to perform that well, depending on what it is that you're asking it to do and the order of constructs and deconstructs you're doing. I didn't want to make this a talk about internal implementation of all these. I'm trying to focus more on the actual uses of them. And finally, another one that's been implemented, and you might not think of this as a linear structure, usually, but it really is, because it's implementing the head-tail signature, and it's got the sequence component also, and it's a heap, which is an ordered sequence. So like a list or any of the other list-like structures, you can see the first element in it. The rest of the elements are a big mystery. In fact, they're not in the same order that you constructed them. They're now sorted. Deletions. So actually, Okazaki, he talks about you can use two heaps in a composite data structure to implement deletions. And I'll leave it at that, and you can maybe think about how you would do that, or talk to me later about it, and I can tell you. A few others that I haven't seen implemented yet. I've thought about some of these. A random stack, that would also be a linear data structure. And another one that I have yet to see implemented that would be kind of interesting is a purely functional circular buffer. So that would also be really, it would adhere to everything we talked about, in terms of implementing sequence and having the signature, either the list-like or its dual signature or both. And that's a potentially interesting structure, but like I said, I've never seen it implemented. So that's what I wanted to talk about. I hope I conveyed a kind of notion of how all these structures are related and interrelated, and what you can do with them. And that's it. I'll leave it over to Rachel now, unless someone has some questions.
I have one question. So at one part you had talked about transforming data structures from one to another. Is there any penalty incurred in that? And at what point does the translation sort of negate the performance benefits of the particular data structure?
Practically speaking, they're all pretty fast, because all these data structures were written with in mind the fact that the of-seek function is very important to constructing it. So they all pretty much load about as fast as, almost as fast as a list does, for instance. Yeah. Some are a little slower. A heap would be a little slower because its insert is actually, I think, O log n. But for most of these structures, the time complexity of kind of the functions that they showcase, each one showcases, is usually O1, so it's usually constant time.
Thanks.
Yeah.
Just not so much question as an observation. Just always this. So the purely function data structures are awesome. They're safe. They're fast. But bear in mind, if you want a dictionary, use the hash table, because it's way faster than you'll get any purely functional. And sometimes the array will be your friend, which you've mentioned. So I think it's a balance. It's not a panacea. Probably start with the purely functional data structures as you default, and then look for those dirty data structures when you need to go, if you need to go really fast.
Yeah, that's a very good point. Although I don't consider maps linear data structures, even though you can load them from certain sequences. Usually they're sequences of tuples, right? Yeah. Good. Thanks. Okay. Thank you.